The second case is an infinite potential well. And this is a little bit like we drew before, or very much like we drew before, an infinitely high energy barrier. And inside here we have a position x, and in this side it's a distance L wide, so it's plus L by 2 on this side and then minus L by 2 on this side. And so we're going to use this as our origin right in the middle here for x. And let's suppose that we place an electron or a particle in general right in the middle of this well. And this potential means that it would require an infinite potential to come over on this side and get out of this well. And of course that's an impossibility. So what this potential well means is ultimately it's going to bound it and keep it strongly inside the wall. So let's suppose that a single electron is placed inside the infinite potential well. All right, so the walls are infinitely high and the electron is trapped. So let's think about this. The probability of finding the electron, and I'll just say e to the superscript minus, of finding that electron out here. So finding it outside is 0. Well, what does that mean? It means that the probability of finding it outside is 0. And that's for x as greater than or really equal to the L over 2 dimension. Right? So the probability is actually 0 to find it out on either side. So what does that imply? Well, this is a boundary condition, and this implies that the wave function itself also equals 0 at the two boundaries. Well, at and beyond the two boundaries, I should say. Okay, so now let's apply Schrödinger's equation to this circumstance. And the solutions are not that bad, but they're slightly more complicated. The solutions to those boundary conditions are something also you've seen in prior classes, but I'll just write them down here. I think you can remember that you've seen them before, but basically instead of just a simple complex exponential, it's sines and cosines. And here we have a, b, and k are all constants. And we can verify that this turns out to meet and solve Schrödinger's equation, but please do that on your own yourself. Just put this into the equation and see that the two terms add up to equal to 0. And also you'll see that you can find that the energy of this solution and of this circumstance is equal to h bar squared times k squared divided by 2m. And in this situation also, the energy is purely kinetic energy because the potential of the particle is 0. All right, so how do we do this? Well, we can begin to apply explicitly into Schrödinger's equation, the solution was that the wave function equals an amplitude times sine, a sine function, plus an amplitude b times the cosine function. And we have boundary conditions. Well, what does that look like? Well, that means that at the left side boundary, that has to equal 0. And that equals then minus sine out here because it's a sine function, and of course this was minus L by 2, so the minus sign comes out here, and then we have b times cosine k L over 2. And here there's no minus sign because the cosine is even. If the inside is negative, then it's the same as if it is positive. Now the other boundary is like it, but with an important difference, and that's of course that the first term has a plus sign. And we can, of course, add and subtract these two boundary conditions, and what do we get? Well, if we add them, we wind up getting b cos L over 2 equal to 0, and a sine, the amplitude a, of k times L over 2 equals 0. Okay, so this is what we must satisfy. So if that's what we must satisfy, we have two options. The first option is that the first amplitude is 0, and the second amplitude, the first amplitude is 0, and the second term leads to cosine of k times L over 2 is equal to 0. And this leads to a bunch of solutions that say that k times L divided by 2 are odd multiples of pi over 2. And of course that means that that's one solution. And then there's a second solution or a second situation when the amplitude b is equal to 0 and the sine component of the other term is equal to 0. And this means that even multiples of pi over 2 are equal to k times L over 2. And so we have all the odd multiples here in this solution and all the even multiples on this solution. So actually we have all multiples of pi over 2 are solutions, and that tells us that k can take on values of n, where n is an integer times pi over the distance L. And n is an integer, of course, that equals 1, 2, 3, etc. So isn't it interesting that all we've done is applied Schrödinger's equation. Let's remind ourselves what we've done here. Let's go back. And I'm coming in for a landing, so stick with me. In this infinite potential well, with these boundary conditions, we have applied Schrödinger's equation and found that not only do we know the solution, which was this, but that solution leads to the k values where they're integer multiples, which of course means that the solutions are quantized. Wow, how interesting. So if we go back to this map, as we drew before, we have values where n is 1, and then we have another energy level where n is 2, for example, and n is 3. And so we can draw the solutions for each of those energy levels as we did in the other cases we've considered already. All right, so what does this mean in terms of momenta? Well, let's write that down for the infinite potential well. Well, this k constant, the wave number, in fact, it's called, takes on these values, and the momenta for that integer or quantum state is equal to h bar times k. And of course, k depends on n. And don't forget that h bar is equal to h, Planck's constant, divided by 2 pi. All right, so if we put these two together, we wind up with the momentum for the quantum state n is equal to n times h over 2L. So what does this mean? Only discrete values are allowed. And so momentum is quantized in this potential well, in this situation. What about wavelengths? Let's talk about the wavelengths of a particle in a well. This seems like a strange thing to talk about, but it certainly is part of this story. So the allowed wavelengths can be found from the momentum. So if the momentum is the quantum number n times Planck's constant over 2L, then we can find the wavelengths associated with that particle are the Planck's constant divided by the momentum of that quantum state. And we can keep on going and find that the wavelengths are 2 times the dimension L of the potential well divided by an integer n. And remember that this well width is the dimension L. And I hope you remember back to our string illustration and analogy that in fact the wavelengths of those allowed standing waves were exactly this expression. So these are quantized. Right? All right, so the momenta are quantized, the wavelengths are quantized, and then finally the energy levels are quantized. All right, so how do we get that? Well, here we have the momentum that we saw before. We know that that is the quantum number n, and we can always find the the energy of a particle, if we know its momentum, as the square of its momentum divided by 2 times the mass. And in this case, that leads to some constants times the quantum number squared. So now energy of a particle in an infinite potential well is quantized. And now we see that it's a square dependence, as I mentioned when we started this discussion. All right, so momentum's quantized, wavelengths quantized, energy levels are quantized, and now I'd like to show you a nice illustration of what that looks like for a particle in a well. All right, so this is what we already drew in our notes, and I'm comfortable showing this to you, and we can see this is an illustration of the wave function. This is the square of the wave function, and here we have the quantum numbers and the quantum states, and we see how it scales, that this is 4 times the lowest quantum state, this is 9 times, this is 16 times. All right, remember, this is an infinite potential well. And as an example, we can see that the ionization energy that's needed to depart from the atom, which I think we've already discussed in a prior lecture, is this 13.6 eV, but it's actually divided by the square of n. And that's kind of the inverse of this, but it's a point of comparison. All right, now that was an an infinite potential well, the last thing I'd like to talk about very briefly is just to show you a slide I prepared on the finite potential well. In this case, what we have is a potential well with a finite amount of energy, which is not infinite. And of course, this is what we can actually make. We generally cannot make exactly infinite energy wells, but we can often approximate it. But in this case, what I'm showing is a finite potential well. So notice that this is a particle that has a finite number of energy levels. Still, we're not going to go through the solution, but even so, this still has quantized energy levels, quantized momentum, and wavelengths. Now, in this case, the interesting thing is that the particle is not bound to the potential well anymore because this is not infinitely high. And so there's a finite probability, and this is the interesting bit that I want to start to hint, we'll pick it up later. There's a finite probability that we will find the electron outside the well, and that's what this illustration shows. This is an infinite potential well, and this is a finite potential well. And what this means is in these regions outside the well itself, there's a non-zero probability of finding the electron. So if you have a wall that is holding in a particle, there is some finite chance of finding it inside or even beyond the wall. That should be very surprising. So the point is that there's a finite probability of finding an electron that is inside a finite potential well, actually outside that potential well. All right, and that leads us to this last topic before we end here, and that of tunneling. For example, an electron on the left side of a wall that is finite in height. All right, and so this is a finite barrier. We see that we can have an electron with a wave function on the left side, and there's a finite probability, as we can see here, or in the wave function, an amplitude that decays, but it doesn't go to zero immediately at this potential wall, such that there's then a smaller amplitude over here with a non-zero probability of finding this electron on this side. So the probability is reduced, but it's not zero. Now, if the electron is on this side or this side, it still has the same energy. And so this reduced wave function doesn't change in this scenario the energy of the electron that could be over here, but it does change the probability or the chance of finding it on either side. All right, now we're going to return to electron tunneling in the nanoelectronics chapter especially, but I just wanted to give you a sense of how these things relate. This is tunneling through a potential barrier, a wall. This is a finite potential well where we show a picture of how we can see the wave function extending beyond the edge of the potential well, so there's a finite chance of finding it there. And then this is the infinite potential well where there is no chance of finding the electron anywhere except inside. And even inside, there's a dependence on distance, on where we're going to find it, or space in x. And we reviewed this case with Schrodinger's equation and found some expressions for the quantized energy, wavelength, and momentum.